the nearest star is still almost unreachable. And that is the whole problem. When people hear Alpha Centauri, they usually think of one star, one point in the sky, one simple destination. But that is not really correct. Alpha Centauri is a star system. The two main stars are Alpha Centauri A and Alpha Centauri B. They orbit each other. Then there is Proxima Centauri, a smaller red dwarf, which is gravitationally linked to them. And Proxima is actually the closest individual star to Earth. That matters because the exact target changes the number a little. If you mean Proxima Centauri, the distance is about 4.24 light years. If you mean Alpha Centauri A or B, the distance is about 4.37 light years. So when people say the distance to Alpha Centauri, they are often mixing together the nearest stellar neighbourhood with the exact target inside it. That sounds like a small detail, but it already tells you something important. Even the nearest star beyond the Sun is not a simple place. It is a system. It is a real destination with real separation inside it. And yet, from Earth, all of that still counts as nearby. But before we continue, please subscribe to the channel to give your support. Let's continue. 1 light year is the distance light travels in 1 year through vacuum. That is about 9.46 trillion kilometers, or about 5.88 trillion miles. So 4.37 light years becomes about 41.3 trillion kilometers. In imperial units, that is about 25.7 trillion miles. That is the first hard reality. Those numbers are so large that they stop feeling like distance in the normal sense. A road trip is measured in kilometers or miles. A flight across an ocean is measured in thousands. Even a trip to the moon still fits inside numbers your brain can work with. But Alpha Centauri is in the tens of trillions. At that scale, normal travel language starts to break. And that is exactly why this topic hits so hard. The problem is not just that Alpha Centauri is far. The problem is that it is the nearest star system beyond the Sun. This is not a difficult example picked on purpose. This is the easiest one. This is the best case. That changes the whole tone of the subject. If the nearest stellar system already means more than 41 trillion kilometers, then interstellar travel is not just a larger version of ordinary space travel. It is not like going from airplanes to faster airplanes. It is not even like going from Earth orbit to Mars. It is a different level of problem. That is the part many people underestimate. They hear nearest star, and the word nearest sounds comforting. It sounds manageable. It sounds like the first small step. But in astronomy, nearest does not mean close in the human sense. It only means less impossible than everything else. And once you see that, the whole Milky Way starts to look different. If the first step beyond the solar system is already this severe, then the galaxy is not some open map, waiting for us to move through it. It is a structure built on separation. The stars are not packed together in any practical way. They are divided by huge gaps. There is also a deeper reason Alpha Centauri works so well as a reality check. Human intuition is not built for this scale. Your instincts are built for bodies, roads, cities, weather, coastline, buildings. At the upper end, maybe mountains and continents. You can stretch that intuition to planetary size if you really try. The Sun already feels huge. The solar system already feels enormous. But Alpha Centauri exposes the limit of that intuition very fast. Light is the fastest thing in the universe. It moves at about 299,792 kilometers per second, or about 186,282 miles per second. And even light needs more than 4 years to get to the nearest star. That is not just a fact about astronomy. It is a fact about how badly human instinct fails on cosmic distance. Because when you hear that, the solar system starts to shrink. The Sun no longer feels like the center of some giant domain. It starts to feel local. Earth feels smaller, the planets feel closer together, and the region between stars stops sounding full. It starts sounding empty. That emptiness matters. Space between stars is not crowded. It is not full of useful checkpoints. It is mostly distance, mostly vacuum, mostly cold separation. And that is why Alpha Centauri is so effective as a topic. It is nearby enough to feel relevant, but far enough to show you how limited our current reach really is. So this is the main idea that controls everything that comes next. The real obstacle is distance itself. Not mystery, not lack of maps, not knowing where to go. Distance. Our probes are too slow because the distance is too large. Human crews become unrealistic because the travel time becomes too long. Communication becomes strange because every signal takes years. Even advanced future engines still run into the same basic problem. The target is simply too far away for our current level of civilization. And that is why Alpha Centauri is terrifying. Not because it is exotic, not because it is hidden, not because it is at the edge of the universe. It is terrifying because it is nearby, and still almost beyond reach. The nearest star is already far enough to make our best machines look slow, our best plans look weak, and our normal sense of distance look useless. And that raises the next problem. If the nearest star is this far away, then how big does our own solar system really look when you compare it to interstellar space? The solar system already feels huge, until you compare it to the gap between stars. Start with distances that already seem extreme. The Moon is about 384,400 kilometers from Earth, about 238,900 miles. That is far enough that light takes a little over 1 second to cross it. The Sun is about 149.6 million kilometers away, about 93 million miles. Sunlight takes about 8 minutes and 20 seconds to reach Earth. Neptune is much farther out, around 4.5 billion kilometers from the Sun, or roughly 2.8 billion miles. Those numbers already feel enormous in normal human terms. Most people will never travel more than a tiny fraction of that kind of distance in their whole lives. So when you hear numbers like that, it is easy to think you are already dealing with the biggest scale that really matters. But then Alpha Centauri appears, and the scale breaks. Because Alpha Centauri is not a little beyond Neptune. It is not at the edge of the planetary map with one last push needed to get there. It is on a completely different scale. Neptune sounds far away because it is far away. But Alpha Centauri is not just farther. It belongs to a different category of distance. That is where the real shock begins. A trip to the Moon is one thing. A trip to Mars is another. A mission to Jupiter or Saturn already feels like serious deep space. Neptune feels like the outer dark edge of the known neighborhood. But even after you pass Mars, Jupiter, Saturn, Uranus and Neptune, you have still not meaningfully approached Alpha Centauri. You have barely started. That is the part people usually do not feel at first. Reaching the planets is hard. Leaving Earth orbit is hard. Reaching Mars is harder. Reaching the outer planets is harder still. All of that is true. All of it takes major engineering, massive launch systems, precision navigation, and years of travel. But all of it is still happening inside our own local system. It is still inside the Sun's domain. It is still home territory on the cosmic map. And that means the terrifying part is not the planets. It is what comes after the planets. Because the planets do end. The neat textbook picture with the Sun in the middle and the world spread around it, that does not go on forever. Beyond Neptune, you enter the Kuiper Belt, a broad region with icy bodies and dwarf planets. Farther out, you reach the zone shaped by the solar wind, the heliosphere, where the Sun's influence still pushes into interstellar space. Far beyond that, in theory, there is the Oort cloud, a vast and distant reservoir of icy objects, maybe extending tens of thousands of astronomical units from the Sun. And even that is still not Alpha Centauri. That point matters more than it seems. First, the planets turn out to be a small inner region. Then the classical solar system turns out to be only part of the story. Then even the outer comet reservoir, the huge, loose shell that may surround our system, still does not get you to the nearest star. So every time you think the map is ending, the map keeps going, and the target is still beyond it. That is how the scale keeps getting worse. A good way to make this feel real is to crush it into a simple model. Take the Earth-Sun distance, 1 astronomical unit, and shrink it down to 1 meter. On that scale, Earth is 1 meter from the Sun. Neptune would be about 30 meters away. So now the whole orbit of Neptune fits inside the length of a large room, or maybe across part of a street. The outer Kuiper Belt would be a bit farther, still manageable, still local. But Alpha Centauri, on that same scale, would not be 40 meters away, or 400 meters away. It would be around 276 kilometers away. about 171 miles. That is the distance from one city to another. That is a major drive. So in this model, if the Earth-Sun distance is reduced to the length of a long stride, the nearest star is still hundreds of kilometers away. That is what interstellar space actually is. Not a crowded field. Not a chain of nearby stars packed tightly together. Not a place where one system smoothly blends into the next. It is mostly separation. Mostly emptiness. Mostly distance. And that changes how you see the solar system itself. Because before this comparison, the solar system feels like the big thing. It feels like the giant map. The outer planets feel remote. Neptune feels like the far edge. But after this comparison, the solar system starts to look compact. It starts to look like a dense local pocket, a small island of matter around one star, floating inside much larger emptiness. That is the real correction Alpha Centauri forces on you. It does not just add one more big number to a list. It changes the scale of the whole list. Inside the solar system, distance is harsh, but still somewhat intuitive. Light minutes, hours, years for probes sometimes. Big numbers, but still numbers you can attach to a system that feels connected. Between stars, distance becomes something else. It becomes a structural fact of the universe. It is no longer just how far one object is from another. It becomes the main condition that controls everything. Travel time is controlled by it. Communication delay is controlled by it. Mission design is controlled by it. Energy cost is controlled by it. Shielding is controlled by it. Reliability is controlled by it. Human psychology is controlled by it. Even your expectations have to be controlled by it. Because if your expectations stay at solar system scale, they will be completely wrong. That is why this comparison matters so much. The distance to Alpha Centauri is not just another large number after the Moon, Mars, Jupiter, and Neptune. It is the point where the map stops behaving like a bigger version of home. It is the point where space stops feeling full and starts feeling divided. And once you see that, another question appears. If the nearest star is separated from us by a gap this severe, then how do we even know that distance so precisely? And why do astronomers stop using kilometers and start using light years? How do you know a star is more than 4 light years away if no one has gone there? That distance is not a guess. It is not a rough story astronomers repeat because it sounds good. For nearby stars like Alpha Centauri, the distance comes from geometry, real measurement, real angles. The method is called parallax, and the idea is simple. As Earth moves around the Sun, your viewpoint changes. So a nearby star appears to shift very slightly against the much more distant background stars. Not because the star is really moving back and forth like that, but because you are looking from different positions during Earth's orbit. It is the same basic effect you get when you hold up one finger and look at it with one eye, then the other. Your finger seems to jump against the background. Nearby objects shift more. Distant objects shift less. Astronomers do the same thing with stars, just on a much larger scale, and with much more precise instruments. Earth's orbit gives them the baseline. The tiny apparent shift gives them the angle, and from that, the distance can be calculated. So when we say Alpha Centauri is about 4.24 light-years away for Proxima, or about 4.37 light-years away for Alpha Centauri A and B, that is not poetic speculation. It comes from the same kind of geometry used in land surveying. The difference is that the baseline is as large as Earth's orbit around the Sun, and the angle is unbelievably small. And that small angle is part of the story too. The farther away the star is, the smaller the shift. For stars beyond a certain range, the movement becomes extremely hard to detect. But Alpha Centauri is close enough that this method works well. So the distance is not just believable, it is measured. Then another question comes up. If kilometers are precise, why do astronomers keep switching to light years? Because kilometers are exact, but they stop being useful when the numbers get too large. You can say Alpha Centauri is about 41.3 trillion kilometers away. That is correct. It is precise enough, but it is also the kind of number that most people stop feeling after the first few digits. It becomes a block of scale without meaning. That is why light years matter. A light year is not a vague astronomy word. It is a unit of distance. It means the distance light travels in 1 year through vacuum. So when you say Alpha Centauri is 4.37 light years away, you're still talking about distance. But now the number carries a second meaning. It tells you how long even light needs to cross the gap. That changes the whole tone. 41.3 trillion kilometers sounds huge. 4.37 light years sounds worse. Because now you are not just hearing distance. You are hearing delay. You are hearing the built-in speed limit of the universe. Light travels at about 299,792 kilometers per second, or about 186,282 miles per second. That is almost impossible speed by human standards. It can circle Earth more than 7 times in 1 second. It reaches the moon in a little over a second. It reaches the sun in a bit more than 8 minutes. And even at that speed, it still needs more than 4 years to get to the nearest star. That is why light years matter so much. The unit itself carries difficulty inside it. The moment a destination is measured in light years, you are no longer dealing with normal travel intuition. You are measuring a gap in terms of how long the fastest thing in the universe needs to cross it. And nothing with mass can simply cruise at the speed of light. Not a probe. Not a human ship. Not any normal vehicle you can just build with better engineering. So the unit already tells you something important. If light needs years, you need longer. That is why a target measured in kilometers sounds distant, but a target measured in light years sounds fundamentally remote. The second one forces you to think about limits, not just scale. And there is another misunderstanding that shows up here. People hear that Alpha Centauri is 4.37 light years away, and they turn it into a visual fact. They say, okay, that means we are seeing it as it was more than 4 years ago. That is true, but that is also the easy part. Seeing a star is cheap compared with reaching it. Observation only requires photons to arrive. The universe does that part for free. The light leaves the star, travels through space, and some of it reaches us. We build telescopes, collect it, and learn from it. Travel is completely different. Travel means sending mass. It means energy, guidance, shielding, communication, durability, navigation, and survival across the whole distance. Seeing Alpha Centauri is astronomy. Reaching Alpha Centauri is engineering. Those are not even close to the same challenge. That contrast matters because it explains why space can feel deceptive. We can study stars, measure them, map them, classify them, detect planets around them, and still be nowhere near being able to visit them. The universe lets us look far more easily than it lets us go. So in one sense, Alpha Centauri is close. In astronomy, it really is close. The Milky Way is about 100,000 light years across. Against that scale, 4.37 light years is local. It is next door in galactic terms. But engineering does not care about galactic terms. Engineering cares about the actual trip. It cares about what has to move, how fast it has to move, how much energy that needs, how long systems must survive, and what happens when something breaks halfway through a mission that takes decades or longer. A bridge does not become easy because the continent is small, compared with Earth. A ship crossing an ocean does not care that the ocean is small, compared with the planet. And a spacecraft does not care that Alpha Centauri is close compared with the diameter of the galaxy. From an engineering point of view, 4.37 light years is still brutal. That is the key correction. Near in astronomy does not mean near in practice. It does not mean reachable with current tools. It does not mean a serious mission is around the corner. It only means closer than the others. And that brings you back to the main point again. The distance to Alpha Centauri is not mysterious because we do not know it. We do know it. Very well, the distance is terrifying because once you measure it honestly, and once you express it in a unit that includes the universe's speed limit, the problem becomes even clearer. The nearest star is not unknown. It is known, measured, visible, and still almost unreachable. And once that is clear, the next question gets much harder. If we know the distance so well, then how do our fastest spacecraft look when you compare their real speed to a target this far away? Our fastest spacecraft sound unbelievably fast until you compare them to the distance between stars. Look at what humans have actually built. Voyager 1 is moving away from the Sun at roughly 17 kilometers per second, about 38,000 miles per hour. New Horizons reached very high speed too, especially for a mission to the outer solar system. Parker Solar Probe goes much faster during its close passes around the Sun, reaching around 100 per 90 kilometers per second, more than 430,000 miles per hour. Those numbers are real. They are huge. On Earth, they sound almost absurd. A galloping horse might reach around 70 kilometers per hour, about 45 miles per hour. A rifle bullet might move at around 0.8 to 1 kilometer per second. Even high-speed aircraft are nowhere close to these probes, so by normal human standards, these machines are incredibly fast. But that is exactly where the trap is, because interstellar distance does not care about normal human standards. It does not care that a spacecraft is faster than a bullet, faster than a jet, faster than anything you have seen moving on Earth. It only cares about one thing: how long the trip still takes. And that is where the numbers become brutal. Take Voyager 1. At roughly 17 kilometers per second, a trip to Alpha Centauri would take around 75,000 to 80,000 years, depending on the exact target and the path. That is longer than recorded human civilization, longer than agriculture, cities, writing, kingdoms, empires, all of it. If Voyager 1 were aimed perfectly at Alpha Centauri, which it is not, it would still be a mission on the timescale of prehistory to a very distant future. Now take Parker Solar Probe. Its peak speed is much higher, around 190 kilometers per second. That sounds like it should change everything. And it does change the number, but not enough. Even if a spacecraft could somehow keep that speed in the right direction for the entire trip, which is a huge and unrealistic assumption, the journey to Alpha Centauri would still take thousands of years. That is the second major shock after the raw distance itself. The fastest machines we have ever launched do not make Alpha Centauri look difficult, but possible. They make it look almost absurdly far. And that is where people often get fooled by space speed. Spacecraft velocities sound dramatic because space has no air resistance, and orbital mechanics can produce huge speeds relative to Earth or the Sun. So a mission to Jupiter can sound heroic, and it is heroic. A mission to Pluto can sound almost impossible, and it is a huge achievement. But interstellar travel destroys that feeling very quickly, because a speed that is amazing inside the solar system is still tiny compared with light speed. Voyager 1, at around 17 kilometers per second, is only about 0.0057% of the speed of light. Not 5%, not even 0.5%. About 0.0057%. That is the scale that matters. So when people hear about our fastest probes, they should not think we are getting close. They should think we are still effectively crawling. On an interstellar scale, our fastest spacecraft are not racing toward the stars. They are barely moving. That sounds harsh, but it is the honest comparison. And the gap is not small. It is not the kind of gap you close with one better engine design, or lighter materials, or a more efficient fuel mix. Getting from 17 kilometers per second to even 30,000 kilometers per second, which is about 10% of light speed, is not an upgrade in the normal sense. It is a leap across multiple orders of magnitude. That kind of jump is hard to explain with everyday comparisons, because everyday comparisons are too small. It is not like improving a car into a faster car. It is not like building a better airplane. It is more like comparing completely different eras of capability. One number belongs to where we are. The other belongs to a level of propulsion we do not know how to sustain. And this is the moment where the whole subject stops sounding like astronomy trivia, because 41.3 trillion kilometers is abstract by itself. You can hear the number and know it is large, but still not really feel it. The distance becomes real only when you place it next to the speed of actual hardware. The moment you do that, the problem becomes sharp. Now, you are not just talking about a distant star. You are talking about a mission that outlasts civilizations, a machine that must survive longer than languages, a trip so long that history itself becomes part of the engineering problem. That is what Alpha Centauri does to modern spaceflight. It exposes the difference between what we can do inside the solar system and what would be required to cross the gap between stars. Inside the solar system, our spacecraft are impressive. Beyond the solar system, they start to look slow in a way that is hard to accept at first. We can cross oceans in hours. We can cross continents in minutes. We can send probes across the planetary system in years. But the nearest star changes the scale so hard that even our best machines stop looking advanced. They start looking early. That is the real pivot point. Up to here, the story can still sound like big numbers and interesting space facts. But once you compare the actual distance to the actual speed of our probes, the tone changes. Now it becomes an engineering reckoning. Alpha Centauri is not just far away, it is a test. A test that our current technology fails by an enormous margin. And once you see that, the next question gets even more serious. If our spacecraft are this slow, then the real enemy is not just distance, it is the energy and fuel needed to push any useful mass to speeds that could matter. Distance is only half the problem. The other half is what it costs to move mass fast enough for that distance to matter. A long trip is not automatically impossible. Humans can wait. Machines can last for years, in some cases even decades. But Alpha Centauri changes the problem, because distance and speed are tied together. If you want to reach another star in a humanly meaningful amount of time, you cannot just keep drifting at ordinary spacecraft speed. You need a very large fraction of light speed. And the moment you ask for that, energy becomes the real enemy. Because speed gets expensive very fast. The energy needed to accelerate something does not rise in a simple way. It rises with the square of speed. That means if you double the speed, you do not need double the energy. You need 4 times the energy. If you triple the speed, the energy does not triple. It jumps by a factor of 9. That squared increase is where the problem turns brutal. So now take a small example. Not a giant starship. Not a human crew. Just a probe with a mass of 1,000 kilograms. About the mass of a small car. If you want to accelerate that probe to 10% of light speed, about 30,000 kilometers per second, the energy needed is around 450 quadrillion joules. That is an almost stupid amount of energy for something that small. And that number is only for acceleration, only for getting it up to speed. It does not include slowing down at the far end. It does not include shielding. It does not include onboard systems. It does not include waste heat. It does not include inefficiency. It does not include life support. Because there is no crew in this example. So even this stripped down version is already extreme. To make that more intuitive, the energy is comparable to more than 100 megatons of TNT for one small probe. Not a colony ship, not a battleship-sized machine. One payload roughly the mass of a car. And the situation gets worse immediately when the payload gets heavier. Double the mass and the energy doubles. Raise the speed and the energy climbs even faster. Add shielding, instruments, communications gear, braking systems, structural strength, and now every kilogram starts to hurt. That is the key feeling people need to understand. In interstellar travel, every kilogram becomes a punishment. Then you hit the next wall. It is not enough to have energy in theory. You also need a way to turn that energy into thrust. And with normal rockets, that becomes a nightmare very quickly. Traditional rockets work by carrying propellant and throwing it backward. That is how they move forward. This is where the rocket equation comes in. And the rocket equation is cruel, because the more fuel you carry, the more mass you have to accelerate. But if you have more mass, you need more fuel to accelerate that extra mass. And then that added fuel has its own mass too, so now you need even more fuel to push that. It is a loop, a bad one. For ordinary missions, this is hard but manageable. Chemical rockets can get you off Earth. They can send probes to other planets. They can do amazing work inside the solar system. But interstellar travel pushes this system past the point where it makes sense. Because to get to Alpha Centauri in a useful amount of time, you need speed so high that chemical propulsion starts to collapse under its own logic. The mass ratios become absurd. The spacecraft turns into fuel for carrying more fuel for carrying more fuel. At that point, the payload becomes a tiny fraction buried inside a mountain of propellant. And even that still may not get you anywhere near the speed you need. So when people say, why not just build a bigger rocket? That question misses the scale of the problem. Bigger does not solve this. bigger can make it worse. A bigger rocket means more mass. More mass means more fuel. More fuel means even more mass. And once you push toward interstellar speeds, the whole system becomes self-defeating. Then there is another problem people often skip over. Speeding up is only half the mission. A fast flyby is one thing. You fire a tiny probe across the void, let it race through the target system, grab a little data, and keep going. That is already hard. But actually arriving in a controlled way is much harder. Because now you have to slow down too. That means the propulsion problem is not one wall. It is two. First, you need the energy to accelerate. Then you need the energy, or some other braking method, to decelerate. If you want to orbit a planet, enter the system properly, send a lander, or do anything beyond a brief high-speed pass, you must get rid of all that velocity at the far end. And that is not a minor technical detail. That is half the mission. A probe blasting through another star system at a huge fraction of light speed may only get seconds or minutes of useful close-range data, depending on the geometry. That might still be worth doing. But it is very different from arrival in the normal sense. Arrival means control. Arrival means slowing down. Arrival means paying the bill twice. That is why serious interstellar concepts often get pushed toward very small probes first. Once you understand the energy cost, and once you understand how the rocket equation punishes carried fuel, the logic becomes obvious. A gram-scale craft is still difficult. A kilogram-scale probe is still difficult. But they are not instantly absurd in the same way a human ship is. That is why many of the more realistic concepts focus on unmanned probes, sails, or systems pushed by external power instead of carrying all their propellant on board. The smaller the payload, the less hopeless the numbers become. Not easy, just less hopeless. And that is the main point of this section. The distance to Alpha Centauri is not only a question of patience. It is not just, can we wait long enough? It is also a question of whether civilization can produce, control, and direct enough energy to throw meaningful mass across interstellar space. That is the deeper problem. The nearest star is far enough away that time becomes severe, but it is also far enough away that energy becomes violent, fuel becomes oppressive, and normal rocketry starts to break down. And once that is clear, the next part gets even stranger. Because even if you somehow solve the propulsion problem, you still run into the universe's hard rule. The speed of light is not just fast, it is a limit. Relativity sounds like good news, until you realize it is also the rule that blocks every easy solution. The speed of light is not just a very large number, it is a hard boundary built into the structure of the universe. Light moves at about 299,792 kilometers per second, about 186,282 miles per second. And nothing with mass can simply accelerate past that. That changes everything, because it means there is no normal engine upgrade that turns Alpha Centauri into a quick trip. There is no version of a better rocket where you just keep adding power until the problem disappears. The fastest possible signal already takes more than 4 years to get there. That is the limit. That is the flaw. So relativity is not some clever escape hatch. It is the reason the problem is so hard in the first place. But relativity also gives you one very tempting thing. It shows that fractions of light speed change the trip dramatically. At 10% of light speed, a trip to Alpha Centauri would take about 43 to 44 years if you ignore the time needed to speed up and slow down. That is long, but suddenly it sounds like something a human being can at least think about. At 50% of light speed, the trip in Earth's frame drops to about 8.7 years. At 90% of light speed, it falls to under 5 years in Earth's frame. And that is the moment where the numbers can feel almost hopeful, because for the first time, interstellar travel stops sounding like a mission across tens of thousands of years and starts sounding like something that belongs inside one lifetime. That is the temptation. Get fast enough, and interstellar space starts to shrink. But then relativity gives you another twist. At very high fractions of light speed, time starts to behave differently for the travelers. This is time dilation. Less time passes for the people on the ship than for people back on Earth. So if a crew somehow travelled at 90% of light speed, the trip would feel shorter for them than it would for observers who stayed behind. From the traveller's point of view, the path is in a real sense compressed. The distance does not disappear, but the experience of crossing it changes. This is one of the strangest and most powerful ideas in physics. It means the universe does allow a kind of mercy, but only under extreme conditions. And even then, the mercy is limited, because Earth still waits. Mission control still waits. Every message still takes years. A human crew might feel less time passing on board, but the people who launched them would still live through the longer timeline. A colony ship would still arrive in a future Earth that might be culturally and technologically transformed. So time dilation helps the travellers. It does not solve the civilizational problem. Then comes the harder part. The part where the door that just opened starts to close again. Relativity gives shorter travel times only if the spacecraft gets close to light speed. And the closer you get, the more violently the energy demands rise. This is where the hope turns back into severity. A mission at 0.9 C is not just a more advanced version of a mission at 0.09 C. It is not 10 times harder in any normal sense. The energy requirements become extreme. The shielding problem gets worse. Guidance gets harder. Heat management gets harder. Tiny mistakes matter more. Tiny impacts matter more. Everything becomes more hostile. So relativity does help, but only by offering something very expensive. At first it sounds generous. Reach a high enough fraction of light speed and Alpha Centauri becomes a decades-long trip, or even less from the crew's point of view. But then the full cost appears. To get that benefit, you have to pay an energy on a scale that is hard to overstate. That is why relativity does not rescue interstellar travel in the simple way people sometimes hope. It does not make the problem vanish. It just shows the terms more clearly. Physics does not forbid reaching Alpha Centauri. That is important. The universe is not saying no. It is not putting the star outside reality. A journey below light speed is possible in principle. Relativity allows it. But relativity also makes one thing very clear. You do not get practical travel times for free. Every step toward light speed comes with a heavy price in energy, engineering, control, and survival. So the terrifying distance to Alpha Centauri is not some dramatic story humans made up to sound impressed by space. It is a mathematically real obstacle. The numbers are real. The speed limit is real. The cost is real. The universe is not saying never. It is saying pay. Pay in energy, pay in time, pay in difficulty. And even if you could pay that price, another problem waits in the dark. Because interstellar space is not empty enough to be safe. And at those speeds, even dust starts to become dangerous. Space between stars sounds empty, but empty does not mean safe. That is another place where intuition fails. People hear vacuum and think nothing is there. No air, no weather, no friction, no obstacles. But interstellar space is not perfect nothing. It contains thin gas, charged particles, radiation, and dust. Spread out, yes. Extremely sparse, yes, but not zero. And at ordinary speeds, that may not sound dramatic. At relativistic speeds, it becomes a serious threat, because a spacecraft going to Alpha Centauri is not drifting through harmless emptiness. It is moving through a very thin medium at such high speed that even tiny particles can become dangerous. The space is sparse, but the speed is so extreme that the emptiness stops helping as much as you want it to. That is the key point. At low speed, a dust grain is dust. At interstellar speed, a dust grain can become an impact event. Take a microscopic particle, something so small you would barely notice it in daily life. At 10% of light speed, if that particle hits a spacecraft, the energy release can be enormous for its size. What would be trivial at aircraft speed becomes violent at interstellar speed. That is why shielding is not some extra feature you add later. It is part of survival. And this problem gets worse the faster you go. The whole appeal of interstellar travel is higher speed, because otherwise the travel time becomes absurd. But high speed is exactly what turns the medium between stars into a threat. The faster the spacecraft moves, the more dangerous every tiny collision becomes. So now the mission has a new enemy. Not just distance, not just energy, not just fuel. It also has to survive being hit. over and over by small particles and radiation during a journey that may last decades, centuries, or longer. And this is not only about dust. Radiation is already a major concern for long-duration spaceflight inside our own solar system. Cosmic rays and other high-energy particles can damage electronics, affect sensors, corrupt memory, and slowly degrade systems. For humans, they can also damage tissue, increase cancer risk, and create serious long-term health problems. Stretch that across interstellar distance, and radiation stops being a side issue. It becomes part of the core design, because distance multiplies exposure time. The farther the trip, the longer the systems stay under attack. The longer the crew, if there is a crew, stays under attack. The longer every component has to keep working in a hostile environment. That means shielding becomes another mass problem. For a human mission, more shielding means more protection, but also more weight. More weight means more energy needed to accelerate the spacecraft. So radiation protection feeds directly back into the propulsion problem. For an unmanned mission, the issue is different, but still severe. You can harden the electronics, you can build redundancy, you can protect memory and sensors, but all of that adds complexity. It adds mass, it adds failure points, and the mission still has to keep functioning for a very long time. That leads to another brutal question. How long can anything we build actually last? A Mars mission may need systems that survive for months or a few years. An outer planet mission may need systems that survive for many years. But an Alpha Centauri mission may demand hardware that stays functional for decades, centuries, or much longer depending on the propulsion method. That is not a normal engineering standard. Even the best machines on Earth are not built for that kind of timescale. Not engines, not computers, not guidance systems, not communication hardware, not power systems. Normal technology is made for years, maybe decades with maintenance. Interstellar missions may require reliability across spans of time that push far beyond normal design culture. And maintenance is its own problem. On Earth, if something fails, people can fix it. In low Earth orbit, astronauts can sometimes repair systems. In deep space, repair gets much harder. On an interstellar mission, repair may have to be fully autonomous or impossible. The spacecraft may have to diagnose itself, isolate failures, reroute around damage, and keep going without help for an extreme amount of time. So distance does not only stretch the trip, it stretches the definition of reliability. And then there is navigation. A lot of people picture a star as a fixed point. Aim at it, fly straight, arrive. But that is not how reality works. Nothing is perfectly still. The spacecraft moves. The solar system moves. Alpha Centauri moves. Everything is in motion. So a probe launched toward Alpha Centauri is not trying to hit a frozen dot on a map. It has to reach the future position of a moving star system after an immense journey. That means tiny errors matter. A very small mistake in direction at launch can grow into a huge miss over light years of travel. A slight problem in beam alignment, sail orientation, onboard correction, or guidance software can become catastrophic later. The longer the journey, the more those errors accumulate. And if the trip lasts decades or centuries, that means the spacecraft may need to track, update, and correct its path over very long periods while also surviving radiation, impacts, and hardware aging. So the terrifying distance creates a guidance problem too. It is not enough to build a craft that can go fast. It is not enough to give it energy. It is not enough to shield it. You also have to make sure it can stay on course toward a destination that is moving, while the vehicle itself slowly changes under stress over an immense span of time. That is why interstellar travel does not simplify as you go deeper into it. It gets worse. Every solution opens another problem. Go faster, and dust becomes more dangerous. Add shielding, and the mass penalty grows. Extend the mission, and reliability starts to break. Stretch the timeline, and navigation becomes more fragile. And once you see that, the next part becomes even harder. Because if an unmanned probe already faces all of this, then a human mission to Alpha Centauri stops sounding heroic and starts sounding like a biological and psychological nightmare. A human mission sounds like the ultimate achievement until you look at what humans would actually need to survive the trip. For people, Alpha Centauri is not just a propulsion problem. It is a life support problem, a systems problem, a health problem, and eventually a civilization problem. A short mission can carry supplies. A mission to the moon can bring what it needs. A mission to Mars might recycle some water and air, but it can still depend heavily on stored resources. An interstellar human mission is different. If the trip lasts decades or centuries, you cannot just pack more food and call it solved. The ship has to keep making life possible. That means food production, water recycling, air recycling, waste processing, radiation protection, medical care, spare parts, redundant systems, and all of it has to keep working far longer than any crewed mission in history. At that point, the spacecraft stops being just a vehicle. It starts becoming a small artificial world, and that changes the whole meaning of the mission. Now, you are not just launching a crew, you are launching an ecosystem, a tightly balanced, fragile, enclosed environment that has to remain stable for a very long time while travelling through deep space. That is already extreme. Then people bring up the generation ship. On paper, it sounds like a solution. If the trip is too long for one crew, then let multiple generations live and die on board. The original crew launches. Their children continue the mission. Their grandchildren arrive. It sounds grand, it sounds epic, but the details are brutal, because now you are not sending explorers. You are creating a closed human society inside a machine. Multiple generations would be born into a mission they did not choose. They would live inside a sealed environment with limited space, limited resources, limited freedom, and no exit. That creates ethical problems immediately. Who gave them consent? What rights do they have? What happens if later generations no longer believe in the mission? What happens if the culture changes? What if the ship develops deep inequality or social collapse? And those are not side questions. On a generation ship, they become engineering questions. Social stability matters as much as hardware. Education matters as much as propulsion. Governance matters as much as navigation. Resource management becomes part of survival. Cultural continuity becomes part of mission success. That is what the distance to Alpha Centauri does. It drags ethics and sociology directly into spacecraft design. Then there is the other common idea: suspended animation, cryosleep, human hibernation. This sounds cleaner. Put the crew to sleep. Reduce food use. Reduce stress. Make the long trip feel short from the crew's point of view. It is a powerful idea, but it is not a simple fix. Human hibernation on the scale needed for interstellar travel is not a solved technology. We do not know how to put humans safely into that kind of long-term suspended state and bring them back reliably after decades. Cryogenic preservation has even bigger problems. Damage at the cellular level is not a small detail. It is the whole issue. And even if that technology existed, it would only soften one layer of the mission. The ship would still need to function flawlessly for the whole journey. The life support systems would still need to work. The power systems would still need to work. The shielding would still need to work. The navigation would still need to work. Autonomous repair would still need to work. Arrival would still need to work. So hibernation does not erase the distance. It only changes how the crew experiences part of it. Then there is the hardest layer to talk about: human psychology. People are not naturally built for permanent confinement inside sealed systems. Not for years, not for decades, not for generations. Isolation changes people. Monotony changes people. Lack of privacy changes people. Hierarchy changes people. Stress changes people. Grief changes people. Conflict changes people. And on Earth, there is usually some release valve. You can leave. You can move. You can find another environment. On a starship, there is nowhere to go. That makes every social problem harder. Every conflict is trapped inside the same system. Every bad leader is harder to escape. Every mistake in culture or structure can keep growing. Mission drift becomes possible. People may stop caring about a destination they will never see. A closed society can become rigid, unstable, authoritarian, fragmented, or hopeless. So a human mission to Alpha Centauri is not just a physics challenge. It is a long experiment in whether human minds, institutions, and relationships can remain stable inside a machine for a span longer than most countries have existed. That is not a minor concern. That may be one of the main concerns. And then comes one more correction that people often skip. Arrival is not victory. Even if a crew survives the journey, they still have to arrive in usable condition, healthy enough to work, mentally stable enough to make decisions, equipped with functioning tools, functioning systems, and enough stored knowledge to operate in a completely foreign star system. If the plan is just a flyby, that is one kind of mission. If the plan is orbiting, landing, building, or colonizing, the difficulty becomes much worse, because a colony is not just a ship that made it. A colony means infrastructure, shelter, energy, food production, manufacturing, medical systems, governance, long-term survival in a place that may not be suitable for human life at all. So reaching another star is not the end of the problem. It is the beginning of a new one. And that brings the whole section back to the main point. The distance to Alpha Centauri is so severe that it reshapes every stage of a human mission. Launch is hard because of distance. Transit is hard because of distance. Arrival is hard because of distance. Nothing escapes that. And once that is clear, the next step becomes obvious. If conventional human missions are this extreme, then the only serious paths forward are not ordinary rockets at all. They are radical propulsion concepts that push right up against the edge of what physics might allow. Chemical rockets are not the answer, and at this point that should be clear. They are good enough to leave Earth, good enough to cross the solar system, good enough to do serious planetary missions, but they are not good enough to make Alpha Centauri practical. So now the question changes. Not, why do the current methods fail? We already know that. The real question is, what could even count as a serious attempt? Not magic, not faster than light shortcuts, not science fiction tricks, real ideas, hard ideas. The kind that still obey physics and still look brutal, even when they work on paper. The first serious option is fusion. Fusion is attractive for one simple reason. It releases far more energy per unit mass than chemical fuel. That matters immediately. If you want a spacecraft to reach a meaningful fraction of light speed, you need an energy source far beyond normal rockets. Fusion at least enters that conversation. In theory, a fusion-driven spacecraft could push a probe to very high speeds, maybe high enough to make an interstellar mission feel like a mission, not a civilization-long drift. That is why fusion keeps coming back in serious discussions. But the gap between theory and reality is huge. Controlled fusion is already difficult on Earth, inside large stationary systems, with massive infrastructure around them. Turning that into a compact, reliable engine for a spacecraft is much harder. Now the reactor has to work in space. It has to be stable. It has to be light enough to launch. It has to survive for a very long time. And it has to do all of that without failing catastrophically. So fusion is not easy. It is not near term. But it is one of the few ideas that lives in the zone of extreme, not automatically absurd. Then there is antimatter. This is where the numbers become even more intense. Matter and antimatter annihilate each other on contact, and that releases enormous energy. In terms of energy per unit mass, antimatter is one of the most powerful propulsion ideas ever proposed. On paper, that makes it look almost perfect. In reality, it is terrifyingly impractical. Antimatter is not fuel waiting in natural deposits. We do not mine it. We make tiny amounts of it at huge cost. Then we have to store it without letting it touch normal matter. Because if it does, it annihilates immediately. So the problems stack up fast. Production is hard. Storage is hard. Safety is hard. Cost is extreme. Scaling it up to mission level looks far beyond anything we can do now. That is why antimatter matters in this discussion. Not because it is likely soon, but because it shows something important. Even our most extreme physical options still come with massive penalties. Then there is the idea that may be the most realistic for an early attempt, beam sails or laser-driven probes. This changes the strategy completely. Instead of carrying all the propellant on board, you keep the energy source far away. A tiny probe is attached to a very light reflective sail. Then a powerful laser array pushes that sail from a distance. The spacecraft gets accelerated without hauling a giant fuel mass with it. That solves one of the worst parts of the rocket equation. And that is why this idea gets so much attention. A gram-scale probe, in theory, might reach around 20% of light speed. That would cut the trip to Alpha Centauri to around 20 years, followed by more years for the signal to come back. Suddenly, for the first time, the mission starts to fit inside a human planning horizon. But this is not easy either. You would need huge laser infrastructure, extreme precision in aiming, materials that can survive the acceleration and the heat, guidance that works across interstellar distance. And most likely you would have to accept a rapid flyby instead of a slow arrival. That is the trade. You may get there fast, but you may not get to stop. Even so, this is one of the few concepts that feels like a real engineering conversation instead of pure fantasy. Not because it is simple, because it is hard, in a way that still sounds physically serious. And that brings the whole section back to the main point. Even the best ideas do not erase the terror of the distance. They confirm it. Look at the pattern. The concepts that seem remotely serious all live near the edge of what we can imagine building. They need giant infrastructure, or tiny payloads, or decades of travel time, or all three at once. That is not what practical expansion looks like. That is what a civilization-level project looks like. Alpha Centauri is not the kind of place humanity reaches after a few better rockets and some confidence. It may require power systems on a vast scale, precision on a vast scale, patience on a vast scale, and even then, the first success may be a tiny probe that only gets one fast look before it is gone. That is the real lesson of radical propulsion. It does not make the trip feel normal. It makes the difficulty more honest. Because when the only serious pathways involve fusion, antimatter, giant laser arrays, or ultralight probes moving at a major fraction of light speed, the message is not that the problem is almost solved. The message is that the nearest star is hard enough to demand the edge of physics and the edge of engineering at the same time. And that leaves one final question. What does the distance to Alpha Centauri actually mean for us? Not just as engineers, but as a civilization trying to understand its real place in the universe. The biggest lesson is simple. The universe is easy to see and very hard to cross. That may be the deepest truth in this whole story. We can learn a huge amount from far away. We can measure stars. We can detect planets. We can study atmospheres. We can track motion. We can calculate masses. We can map the sky with incredible precision. So in one sense, the universe is open to us, but only to observation. Travel is different. Travel is expensive. Travel is slow. Travel is dangerous. Travel forces you to move matter, not just collect light. And Alpha Centauri makes that difference impossible to ignore. We may understand the stars long before we can ever reach them. That may be one of the defining facts of human life in space for a very long time. Knowledge is cheap compared with movement. Looking is easy compared with going. And that changes how you think about the future. A lot of people jump from moon bases to Mars cities to the idea of humans spreading naturally from star to star. It sounds like a smooth ladder. First one world, then another, then in the galaxy. Alpha Centauri breaks that idea. Because if the nearest star is 4.24 to 4.37 light years away, then the galaxy is not some open landscape waiting for normal expansion. It is not a place you casually move through once you become a little more advanced. It is a place broken up by huge separations. That does not mean interstellar travel is impossible forever, but it does mean it will likely be rare, expensive, and transformative whenever it happens. Not routine, not casual, not the space version of commercial aviation. The nearest star resets expectations. It forces scale back into the conversation. It forces discipline back into the conversation. It removes the fantasy that star empires are just the next obvious step after learning to live on other planets. Then there is the part that hits at a more human level. The terrifying thing is not only danger, it is also loneliness. There is something very hard to ignore once you really understand this distance. The sun's nearest stellar neighbour is still so far away that even light takes years to cross the gap. Not days, not hours. Years. That means our civilization is still, in a very real sense, local, confined, tied to one small region around one star. Yes, the solar system may become a much larger human sphere in the future, That is possible, maybe even likely, over long enough timescales. But Alpha Centauri reminds you that leaving that sphere is not just one more step outward. It is a jump into a different regime, where distance controls almost everything. That makes Earth feel more important, not less. Because once you understand how hard it is to cross the space between stars, you stop treating worlds like they're easy to replace. You stop assuming there is always another one nearby. You stop speaking about the galaxy as if it were already in reach. And that leads to the last hard point. Alpha Centauri is also a test of what kind of civilization we are. Ask whether humanity can reach Alpha Centauri, and the answer is not only about engines. It is about planning, energy, institutions, cooperation, stability, patience. A civilization that cannot build and maintain large scientific systems probably does not get there. A civilization that cannot manage enormous energy use responsibly probably does not get there. A civilization that cannot stay coordinated across long timescales probably does not get there. So the trip is not just a test of engineering, it is a test of maturity. That is why the distance feels so severe. It shows the gap between what we can imagine and what we can actually sustain. Humans can imagine star travel very easily. Reaching a star may require a level of coordination and endurance that we have not yet proven we possess. And that is the final meaning of Alpha Centauri. It is close enough to tempt us, far enough to humble us, real enough to force honesty. The planets in our solar system are hard. The stars are something else. The terrifying distance to Alpha Centauri is not just a number. It is the point where humanity finds the edge of its current reach and sees how much farther reality goes. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.